Okay, so welcome back everyone. Today we'll go more into circuits as you did yesterday in the afternoon session. Just this time is going to be circuits with extra features on top of them, or more specialized circuits. So we'll start with synaptic plasticity and reinforcement learning. So in other words, we will model circuits with learning rules or synaptic plasticity rules in them that adapt over time. Now, the synaptic plasticity in general is the adaptations that happen within synapses, and as we saw yesterday morning, synapses is how neurons communicate with one another, right? So when we say that one synapse is potentiated or becomes strengthened, then it's easier for a presynaptic neuron to communicate spikes to a postsynaptic one. And likewise, depression or weakening the synapse is the opposite of this. And we can have different synaptic mechanisms working on different time scales within the brain, from milliseconds to even minutes and longer. And a very classic, rule about synaptic plasticity, you probably have heard of this, put forth by Donald Hebb in the 40s, about neurons that fire together, wire together, which in other words means that if the spike times of two neurons are very close to one another, and these neurons are connected, of course, with the synapse, then this synapse would get strengthened. And we will see essentially different flavors of this Hebbian rule today in the exercises. So you have seen this the corticostriatal model in the first day's talk, and partial view of that you have built yesterday, right? And essentially, this model was originally designed to do category learning. And as you might remember, the task with category learning was originating in the macaque literature, where essentially the monkey had to decide whether a specific dot pattern, so a cue like this one, belonged to category left or category right. And these are the two prototypes, where that essentially generated all the stimuli, right? Of course, the monkey had never seen the prototypes, but the challenge was to come up with a categorization rule that can distinguish between these things. So every stimulus here, I should say, is an exemplar, and this is a distorted image of either one of the two prototypes, right? So the animals never see exactly the prototype. So yeah, the animal has never seen the prototype, so they just by trial and error and taking actions and receiving feedback, it has to learn how to distinguish between the two categories, right? And this, we claim, is essentially driven by synaptic plasticity in the animal's brain. And this is what the full corticostriatal model, building neuroblocks, has in it as well. So here I'm just showing you the model again, just to remind you of the structure, and also highlight a few components which have to do with the task, right? So the stimulus coming into the model, this is the image stimulus. You built image stimuli yesterday. So these are the dot patterns coming in to visual cortex. And after the cortex and to the striatum connection to other subcortical regions, we have the final action with this saccade, because the monkey chooses left or right by looking at the left or right direction. And after the action, we also have the behavioral feedback, which is reward or no reward according to the choice made. So these are all part of the model. So we can, within NeuroBlox, model actual behavioral tasks and link them to a circuit model with no problem. And as I mentioned yesterday as well, this model was built on principles about structure and function that we have about the brain, and it was constrained by specific parameters that we got from the literature. It was never directly fitted to data from this task, yet it can match both the physiological elements of the task, as you can see here in the LFP and its spectrogram, and also it can match the learning behavior over time. And it can actually match these both the IFIs and the behavior because of the learning rules that help it adapt over trials. And this model includes both LTP, long-term potentiation, in the cortical synapses, that is the synapses between the visual cortex and the anterior cortex. And then it also includes corticostriatal synapses that can do both LTP or LTD, and these are also modulated by dopamine between the anterior cortex and the striatum here. And we'll get into more detail about these. And as a note, in NeuroBlox, we call these the synaptic rules, learning rules, right? Because this is all in the context of decision making. So yeah, the learning rule is essentially the gradient that the synaptic weights follow to adapt over time. So first, with the cortical LTP, this is a form of Hebbian learning, as you can see here with this term, the LTP, right? The S's here are the activities of the presynaptic and the postsynaptic neuron, and it also includes an extra reversal term, which essentially means that this term is actually dependent on dopamine released in VTA. So what is happening here is that during the trial, there is potentiation happening in the synapses, in the cortical synapses, but in anticipation for the result, for the reward. But maybe if the choice that the animal makes it's wrong, then there is actually reversal of that potentiation mediated by this term here, which happens through dopamine VTA, right? Because whether the animal receives a reward or not, actually drives the dopamine released in VTA, which in turn drives this reversal or no reversal. So here you can see an example of how this plasticity rule drives the weight changes over trials. So here we have simulated 700 trials of the task, right? Each trial is a separate stimulus and one action and one reward feedback. And as you can see, this is an adjacency matrix for the weights between the visual cortex and the anterior cortex. And you can see the weight values changing from the beginning to the end of the task. And likewise, you can see the average weight in these same synapses actually adapting over time and reaching a stable value. So moving on to the second place where we have implemented synaptic plasticity in this model, that is the connections from the anterior cortex to the striatum. So these connections follow a more sophisticated rule, which can induce both LTP and LTD. And essentially this rule, again, the changes in weight, the weight gradient, in other words, it has the typical, Hebbian-like component where, it is a function of the activities of the presynaptic and the postsynaptic neuron. But now this Hebbian component is modulated by the DA, the dopamine released in the substantia nigra. So essentially here we have a third region, this SNC, working as a modulator in the connections between cortex and striatum. And there is also a third term which actually depends on the current values of these weights. And as I was saying before, because of this immediate tie to dopamine, any reward feedback can actually either strengthen the synapses or punishment or omission of reward can also weaken the synapses and induce LTD. And also this rule, you can work out the math, which actually you can see in more detail in this paper as well. If you expand on the dopamine term, which is essentially dopamine released in SNC, right? It has some baseline dopamine plus this epsilon value, and this epsilon value is essentially the difference between the actual reward received and the expected value of the reward to be received, right? And this difference shows up in classic reinforcement learning rules like Q learning, or even in temporal differences learning as well. You can see a flavor of this plus some extra terms. So this is a nice result that highlights the fact that simpler agent models can actually relate to neurobiology through this synaptic plasticity rule. And here you can see a result which is like a parameter search over having two different parameter sets. You can see in fact how varying essentially this prediction error, which is the epsilon, right? The difference between actual value and predicted value. How does this affect the weight gradient, the delta of the W here? And how this can induce, both depression and potentiation, based on the sign essentially of the prediction error. So what we will build here is again a partial view of the full model in two places. Initially, we'll work on a model like the circuit model from yesterday. So two cortical regions, an image stimulus, and an ascending system that modulates their activity. and we will see how behavior plasticity works with no feedback. So we will remove the LTP. There's no LTP reversal, right? Because we'll just let the system simulate and see how it adapts. And in the second example, we will include striatum elements as well. And in this case, I will do proper reinforcement learning with, each image will have a category. There are correct label categories, and the model will have to make a decision on each trial, and we will, judge whether the decision is good or bad, and then adapt the weights accordingly. And you will see how this works. So yeah, this was all. So you can navigate to the Synaptic Plasticity and Reinforcement Learning notebook. And yeah, again, feel free to ask us any questions.